We're now recording. Let's go to current slide. And before we get started on this, let me go over this announcement. Now, they gave me a really scaled down version of the poster. You see these on doors and walls and various places. Coming up in 2 weeks, a little bit less than 2 weeks, Cougar Connection Week. Okay? There's going to be lots of different issues and programs, both campuses, and I'll tell you more about those as we get closer to it. But it's Monday through Thursday of the week of the 17th through the 20th, Monday through Thursday. There will be lots of places where you can volunteer. Those organizations, a lot of them will be on campus, and you can sign up to volunteer. There will be campus organizations that you might want to become a part of, like ambassadors, athletics, fine arts, honors college, PBL, Scholars Bowl, Student Government Association, speech and debate, social student support services, or STEM. Lots of places you can tie in, use your talents. A few of these places actually pay you, like student support services, they'll pay you to tutor, okay? So, in STEM, if you qualify for that, you can get some funding for that, okay? So there's, and actually things like ambassadors, I don't know if they actually pay you, but they give you, there are some benefits to it, you know. I can't remember how they do that. I don't know if it's tuition or something else that you actually get sort of a scholarship to participate in some of these. So lots of good things to tie into, plus some good information will be given. And I believe she said sometime that week they're probably going to have a blood drive as well. So another way you can connect and participate. So anyway, that's the announcement. Let me find out next. Any questions on anything we've done so far? Okay. So where we left off last time, I think we showed, maybe not the first slide, but came close to it. Yes. Yeah. Actually, we did some things at the end of the last mean value theorem, and this leads directly into average value of a function. So let's say the value of f of c, okay, given in the mean value theorem for integrals, is called the average value of f on the interval a to b. So if you remember back what we were saying, let's go back a slide or two. Okay, right here. If you have some function, and it needs to be a positive function, something greater than or equal to 0 on the interval a to b. If you have it there, and you want to know the area under there, sometimes it's tough to do, but you can tell by sort of looking here, as long as a and b are not, it doesn't even mean they have to be, but just the interval here, and this is your function, there's some value c in between a and b, so that the function in between f, the minimum and the maximum, I'll put it that way, it doesn't have to be in between f of a and f of b, but there's some value here that f of c is going to have the same area under it as the curve. See, this rectangle overshoots this much and undershoots that much, and if those two are exactly the same, which there is some value that's going to be the case, then you f of c is the and this is the mean value. All right, this is Vince, right? Okay, there you go. All right, and since it was that c that is the average value, that means that another way to do that is the average value of f on a to b. It's the value of the total function there is the average value of f on that interval. Okay? So, if f is integrable, got to be that, and to be integral, meaning continuous, okay? If f is integrable on a closed interval, a to b, then the average value of f on that interval is, since let's go back to this. Here was your mean value theorem. The integral from a to b, f of x dx, is some value c in between a and b, f of c times a minus b. That's that rectangle. Height f of c, length b minus a. So guess what we do? We divide both sides of the equation by b minus a. You get f of c is equal to 1 over b minus a times that interval. And that's what your average value is. Here it is, right here. The average value is 1 over b minus a. So this is that f of c is equal to 1 over b minus a times the integral a to b f of x dx. That's going to give you the average value of the function f of c. Okay? In this figure, the area of the region under the graph of f is equal to the area of the rectangle whose height is that average value. Okay? Now, again, and this is why I was trying to be very careful, the function has to be positive, greater than or equal to 0. Can't get down here. That we won't mess with that yet. Okay? And I said before, and there's some value c here, that this is f of c. Well, guess what? It's f of that c, f of this c, and f of that c. Any one of them. It doesn't matter which one. But the value, f of c, is this value here. That's what you're interested in. That's the average value. Where the c is, it doesn't matter. It can be this c, that c, or that c. It doesn't matter. The f of c is the same in all three places. That's your average value of the function. Okay? So the other one just showed one place of intersection. This could be several. Okay? And the average value is the length of this rectangle divided by the area under the curve, which is the area of the rectangle, and that's going to be your average value of the function. Now, whatever that value there is, the average value. Okay? Make sense? Okay, kind of. Okay, but I mean, the average of this, the area of that rectangle is the length times the height, right? The length is b minus a. The height is f of c, okay? Which is your average value.
I see you divided that by in the b minus a to the other side by dividing it by 1.
Yeah, right. So you divide by b minus a, and that gives you that average value of the function. This is the area under the curve, which is the same as the area under the rectangle, okay? From the mean value theorem, okay? And then divided by b minus a, and you get the height of this, which is your average value of the function. Okay. Now, to see why the average value of f is defined this way, partition a to b into n subintervals with equal width delta x. Okay? So b minus a over n, that's what we've always said our delta x's were. If c sub I is any point in the I subinterval, then the arithmetic average, or the mean of the function values at that ci, or at the various ci's that you have, because you could have one on any one of those, that average value, I don't like that they said a sub n, because we used a to be the endpoint, but this is the average value, not that a, but the average value is 1 over n, because guess what? If ci is any point on the I subinterval, then the average value of those ci's, so if you, I wish they had a picture here. Let's say that we split this into n equal pieces, right? And then you took a c from here, c from there, c from there, c from there. And you want to average those together. You add up all those c's and divide by n, because remember you had n divisions. So you take the average of those C values. That's all it is. So sum up the C's, C sub i's, okay? Okay, not the C sub I, the alpha C sub I. Okay, so the CI, pick this alpha, that alpha, that alpha, that alpha, this alpha, this alpha. The alpha of all those C sub I, add them all together and divide by n. That's your average of those C sub, alpha C sub i's. Okay, and yeah, the function values at the C sub i's. That's what I missed. Okay, so add up each one of those. You got n of them. So add them all together, divide by n. That's your average value for that, for those alphas there. Okay. Now, by writing the sum using summation notation, then multiplying and dividing, as you were saying by b minus a, you can write the average this way. So the average is 1 over n. Remember, that was here, dividing by n, 1 over n. So that's outside. That's not part of your summation. 1 over n, the summation for I equal 1 to n of alpha ci. C is some point on that. Okay, we're going to multiply by b minus a, also divide by b minus a. Okay? Okay. And for some reason, they did the division out here, which I was expecting, but they moved the n, 1 over n, inside, which is fine. It's just a constant. You can move it inside or out. So why did they even pull it out in the first place? Why didn't they leave it in there? That's what I was trying to figure. Okay, and then this gives you 1 over b minus a, and then this is your summation. But this, remember, is your delta x. B minus a over n is your delta x, and you're summing over this. Well, that's your integral from from a to b, alpha of x dx. That's exactly what our average value was. 1 over b minus a times the integral. Taking the limit as n goes to infinity produces the average value of alpha over that, exactly like I said. The summation becomes the integral from a to b, alpha of x dx. Okay? And then they've shown this picture again and again. Notice that that average value is the area under the curve. Yes, that's what we said it was. That's what we said for the mean value theorem. We've said it over and over. That is the area. Okay? So, that gives you the average value of the function. Have they beat it to death yet? Okay, seems like they have. So let's do one. Find the average value of alpha of x equal 3x squared minus 2x on the interval 1 to 4. So what would be your average value? Let me get my pen set up. What did we just say the average value was? 1 over b minus a integral from 1 to 4, okay, of 3x squared minus 2x dx. Okay, and the only thing is, if we plugged in what a and b were there, let's plug it in here too. So this would be 4 minus 1, right? B minus a. So this would be 1/3. Now, can you take the antiderivative of 3x squared? What? Say again? Okay, I think you're taking the derivative of it. We're antiderivative. Okay?
X to the third over 3.
Okay. Yes, 3x to the third over 3, and the 3's go out. So it's just x to the third minus 2x squared over 2. And the 2's go out. They've been dating. Okay, never mind. Okay. And you evaluate that from 1 to 4. Okay. That's, okay. That would be 1/3. That's out front. And can we evaluate x cubed at 4? What is 4 cubed? Four cubed.
No. 16.
Say again?
16 is
4 squared is 16.
Yeah, so
4
16
cubed
times
is what?
16 times 4.
Which is?
I said 32.
That's all right. That's, say again? That's 64. Double it, okay. 64 minus, and what's 4 squared? 4 squared? 16. And then minus a 1 to the 4th is, I mean 1 cubed, sorry. 1 cubed is pretty easy. 1 minus a minus is plus 1 squared is pretty easy.
1 squared is
1. Okay. All right. Whew, I thought, okay, feel like a dentist here pulling teeth. Okay. The minus 1 plus 1, of course, they add the 0, and 6, that would be 1/3 of 64 minus 16 would be 48, and 3 will go in the 48. 16 times. 16 times. So there's our answer. 16. Let's see. Oh, look at that. That's what they got to. Good for them. Okay. Goodness, I should have eaten something when I went down to my office. My stomach here going, wah, wah, wah. Yeah.
I was writing here. I must have missed it. Where is the -1 plus 1?
Okay. All right. Right. What we had is x cubed minus x squared, right?
Oh, yeah. So you
Evaluate
plugging in the
1
1.
to 4. Yeah. We first plugged in the 4, and that would be 64 minus 16, and then we subtract it when we plug in the 1. So that would be a minus 1 cubed is 1, minus a minus, which is a plus 1 squared is 1. So there you go. Okay. All right, that's how we did it. Let's see how they do it. Okay, the average value is 1 over b minus a times the integral from a to b of f of x dx, plugging in what the a and b are, 1 to 4. That would be 1 over 4 minus 1, b minus a, times the integral from 1 to 4, a to b, of 3x squared minus 2x dx. So that would be 1/3, and then the antiderivative of 3x squared is x cubed, minus the antiderivative of 2x is x squared, and evaluate that from 1 to 4. That would be a 1/3 times 64 minus 16, that's 4 cubed minus 4 squared, minus a 1 minus 1, put in parentheses, that's one way you could do it. And that still comes out being a 0, and that would be, what's that? Yeah, see what? Right, exactly. So if this helps you see it better, you do it this way. What I was doing in my head, that'd be a -1 plus 1. So it gives you the same thing. But we just did 2 steps at once. They did split it up, yeah. Okay? And then that gave you 48/3, which is, of course, 16. And then here's the picture of it. Here's the picture of the graph from this has a value of 1 down here, 1, 1. So you see the scale is way off here. Here's 1, there's 10. Okay, not the same scale, but yeah, understanding that. So here's 1, 1 up to 440, which is a race number. That would be 3 times 4 squared is 16. 3 times that is 48 minus 8 would be 40. So that's where we get 440 from. Obviously, that's expanded compressed the y, expanded the x to get this. And there's the area under it, and that's the same as the area under this plot. That's 4 by 16. I mean 3 by 16. Same area. This area here that overshoots it here is the same as that undershoots it there. You can't tell for sure, but it is. Okay? Does that make sense? That's how you get the average value of a function. I'm trying to think when you ever need that, but we know how to get it if we ever needed it. Okay? Now,
We'll be able to test it, we'll need it then.
what's that? That's when you'll need it, when it's on the test. Right, okay. Okay, cynic. Okay, so let's do example 5. They skipped that one, and this may be a place where you would need it. The speed of sound. At different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, S is a function of X, in meters per second, can be modeled by this piecewise defined function, S of X, speed of sound, and X is your altitude. They don't really say that very well, but that is your, X is your altitude, okay? Talk about a piecewise defined function. It's minus 4x plus 341, and that's anywhere 0 less than or equal to x less than 11.5. Now, I believe that's in meters, okay? Yeah, meters per second, so x would be in meters, okay? It's a constant 295 anytime x is between 11.5 and 22. Okay? Then it's 3/4 x plus 278.5 anytime between x is between 22 and 32 meters. Okay? And it's 3/2 x plus 254.5 anytime x is between 32 and 50. Okay? And finally, it's minus 3/2 x plus 4.5 anytime it's between altitudes between 50 and 80 meters. Okay, that gets you up to 80 meters. Now, interesting thing is, in the first 11.5 meters, the speed of sound is actually decreasing, then it's constant, then it's increasing over the next two intervals and decreases again. Rather bizarre, but true, okay, I guess. They have a little blurb here with one of my favorite pictures, and I've seen several taken like this. That is an aircraft, if you got the book, breaking the sound barrier. But it looks like it's coming out of a cloud, doesn't it? And it really is, because sound is a compression wave, okay? And when you're approaching the speed of sound, you're approaching, and if you're going the same speed the sound is going, then all your compressions are piling up in front of you. They're just, as you're going a little bit slower, they're barely beating you. But when you break it, then you go through, and all those compressions have gathered together all the little water droplets that were in the air and formed a little cloud in front of you. And when you go through that, you're breaking. Now you're going faster than they are, so they all piled up there together, and the plane looks like it's just coming out of a cloud. It's just a neat picture, okay? And I had forgotten this. The first person to fly at the speed greater than sound was Charles Yeager. I recognize his name. Back in 1947. That was 2 years before my older brother was born, so that was before my time. He, because the speed changes with altitude, if he'd have been a little lower, he wouldn't have been exceeding the speed of sound, but at that altitude, he did exceed the speed of sound. Okay, but anyway, there's FA-18F Super Hornet, supersonic twin-engine strike fighter. Okay, blah, blah, blah.
Why is altitude affected?
What's that?
Why is the altitude affected?
Well, several reasons. Number one, as you're going up, the air is getting thinner, and so that affects it, okay? But it's also getting colder, and that affects it. And sometimes the effects are additive, and sometimes they're subtractive, and that's why.
It's weird, huh?
It really is. And that's just a model. That's not exact. In reality, it's a smoother curve, but we don't have the math to define that curve, or it would be a really messy one to define.
So it would take like a lot more power to break the speed of sound on land as opposed to in the air.
Okay, say that one more time.
It would take more power to break the sound barrier on the ground as opposed to the atmosphere.
Yeah, because you got a lot more air resistance. So yeah, so the further up you go, the faster you can fly. But if the speed of sound is increasing as you go up, it may be harder. There's several things. But yeah, you're absolutely right. It takes more. You got a lot less friction higher, and that's why jets go. That's why they fly at those high altitudes, because it's less air resistance. Okay, be very poor fuel economy to try to fly low. In fact, those strike aircraft that do fly low, their range is much shorter because they use a lot more fuel going through that much air. Those bombers that go really high and drop them from really high, they can stay up there a long time because using less fuel. Okay. And then the question here is, X is actually the altitude in kilometers, not meters, kilometers. So that's way up there. That's what the X's are, kilometers. What is the average speed of sound over the interval from 0 to 80? So what you have to do is integrate every one of these from 0. You integrate this one from 0 to 11.5, integrate that, which is real easy, from 11.5 to 22, integrate this from 22 to 32, integrate this from 32 to 50, integrate this one from 50 to 80. Once you've got all those intervals, then divide by 80, 80 minus 0, and that should give the figure. Okay? Now, you want to do all those intervals? You can. Is it good practice? Okay. Let's do them then. All right. I think I'm going to have to erase what's here and use it out of the book because I don't have enough room to integrate all of them on this. So That's what our problem is, so let's erase that and do the integration. So the first one is integrating from 0 to 11.5 and minus 4x plus 341. Okay, what is that antiderivative of that? Yep. Yep. So that would be minus 2x squared, right? Okay. We'll integrate that from 0 to 11.5. Okay. Oops. Whoops. 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 Why were you going to let me get away with that? We didn't integrate the second term. Antiderivative of 341. 341x. That's what we evaluate from 0. That is a 0. It looks like a 4. 0 to 11.5. Okay? Pull out your calculators. I'm not going to do this one in my head. Okay? Minus 2 times 11.5 squared plus 341 times 11.5. Minus 2 times 11.5 squared plus 341 times 11.5. Right.
341. What was the last bit?
Okay. It's minus 2 times 11.5 squared plus 341 times 11.5. $3,657. That's exactly what the book got. Okay? And then we're going to add to that the integral from 11.5 to 22 of 295. Yeah. And that's really simple. Okay? That's 295 times the difference between that, and that's 10.5. Now, I'm sort of cheating a little bit doing that because that's just a constant between those two values, and just the difference between these two times that. That's the value. I'm not doing an integral. You could. There's the 295x evaluated from 11.5 to 22, which would be times 22 minus 11.5, which is 10.5. So it would give you the same thing. What does that give you? 3,000. Oh, yeah, 3,097.5. That's what they got in the book too. Okay, now we're going from 22 to 32, and it's 3/4x plus 278.5. Okay. What's the antiderivative of that?
X squared over 2.
3/4 x squared over 2. So it'd be 3/8 x squared. What's the second part?
Plus 278.5 x.
Okay. Evaluate that from 22 to 32. My head's clogging up. I don't know why. All right. So that's 3/8 times 32 squared plus 278.5 times 32 minus 3/8 22 squared. That's a pretty ugly 2 minus 278.5 times 22. Okay. Got an answer yet? What you got?
2,987.5.
Yeah, 2,987.5. Nice round number. Okay. The next increment is the integral from 32 to 50. And that would be of 3/2 x plus 254.5 dx, which would be antiderivative of 3/2 x. 3/4 x squared plus 254.5 x, evaluated from 32 to 50. Okay, which is 3/4 times 2,500. I can do that one in my head. Plus 254.5 times 50. I probably should do that in my head, but I don't feel like doing it. Minus 3/4 times 32 squared minus 254.5 times 32. Okay, a mess, but a doable mess. Drying out like crazy. Got an answer yet?
5,688.
That's what they got too. 5,688. Now, I don't know if I'm going to have room to write the next one under there. I'm thinking about writing it up top, just because you get into all the stuff at the bottom. I'll try it. Let's see. The integral from 50 to 80. These are kilometers too, by the way. And this one is minus 3 halves x plus 404.5 dx. Okay? What's the antiderivative of 3 halves x, minus 3 halves x?
Minus 3/4 x squared.
3/4 x squared. Perfect. Okay? If it will ever write, there it goes. Plus 404.5 times x. Yeah. I'm going to have to times x. All right. Evaluated from 50 to 80. All right. Oh, goodness, I can't breathe. That's minus 3/4, and 80 squared is 6,400. Okay. Plus, I can't write either, 404.5. The pen is really, really slow here, times 80. And then you got a minus, but it's minus a minus, that's plus 3/4 and 50 squared. Yuck. 50 squared is 2,500. And then you have a minus a plus, which is minus 404.5. I think it is. I can't read my writing. And I'm running out of room, times 50. Okay. That's messy, I know, but I should be able to do a lot in my head. 4 will go into 6,400, 1,600 times, and then minus 3 times that. I'm not going to try. Okay, I can do it, but not today. What does that add to? 9,210. Okay. Now, the next thing we do is add all those up. Now, that's an ugly 10. My pen wasn't writing, so I wasn't sure what it was doing here. Let me see if I can. Yuck. Okay. So you add those up. 3657 plus 3097 plus 2987.5 plus 5688 plus 9210. Okay? Add those up. And then you divide by 80. Why 80? Because you're going from 0 to 80.
get?
269.
Okay, they got 308. What did you get when you added all those up together?
3657 plus 3097.5.
Oh, okay. I left one out. Okay, yeah. That's it. That's it.
Anyone get an answer yet?
308.
308 is what they got. 308. 308 meters per second. And near the surface of the Earth, we usually use 341 meters per second because that's what it is on ground level. But if you include the entire atmosphere, it averages 308. So it doesn't really change a lot as you go up, the average speed. All right.
Most why we divided by 80 then.
What's that?
Why didn't we divide by 80?
Because that was your B minus A. See, here was 0 to 11.5, 1.5 to 22. So you wind up being 0 to 8. So you divide by 8. That's your interval. Your B minus A, 1 over B minus A. All right. That done, exercise in integration and adding and that kind of stuff. We're ready for the second fundamental theorem of calculus. The first one was how you do definite integrals, right? That was pretty straightforward. Do the antiderivative and then evaluate from B minus to A, right? Okay. Second fundamental theorem of calculus is going to use some of the stuff we did before. And earlier you saw definite integral of alpha on the interval B minus A to B was defined using the constant B as the upper limit of integration, x is the variable of integration. However, a slightly different situation may arise when the variable x is used as the upper limit of integration, not b. Now, to avoid using the confusion of using x in two different ways, t is temporarily used as a variable of integration, okay? And remember, that variable is a dummy variable anyway, because no matter what you put in there, the integration will be the same as long as you evaluate it between the same limits. And here's Daniel. All right. Now, we're missing 2. Okay? And they usually come as a pair. Okay, so I don't know if they're going to make it to there or not. Okay, so we usually just throw in a dummy variable. T is as good as A, S, P, Q, anything but X, okay? Remember that the definite integral is not a function of its variable of integration. It's a number. It's a value that you get, okay? So, with a definite integral, the integral from A to B of f of x dx would be the same as the integral from A to B of f of t dt, integral from A to B of f of s ds, the integral from A to B of f of y dy. It's not going to matter because whatever that function is, you're going to integrate it the same way, the antiderivative, and then you're going to evaluate it between those two things. So you're just going to get a number. And the number doesn't depend on what the variable is. Okay. Now, what we're going to do now is rather than having a constant here, we're going to put the variable there, the x, okay? And then we're going to put t's or s or u or stickman. You can put anything in here you wanted to, and you're going to evaluate that from x to a, okay? And basically, the antiderivative here is going to give you your f of x because the a, it really, in a sense, doesn't matter what that, well, it'll just be a constant. Yeah, okay. This is just a dummy variable you integrate out. Okay. When you put the values in. Okay. I think doing is believing, not seeing is believing. Doing is believing. So let's do one. Evaluate this function, f of x, as a function of x, because your variable x is in the up. Okay. And this is going to be from 0 to x cosine t dt. Okay? And we're going to do it at 5 different values of x. Okay? So let's first do it for x. Okay? So what's the antiderivative of cosine t? What's that?
I always get confused on these.
Okay.
On the trigonometric function.
Okay? We'll give it a shot. Second? It's going to be sine of t. And how do you check that? You take the derivative of sine t and you get cosine t. Okay? So yeah, that is the correct thing. But you're going to evaluate this from 0 to x. And at first, when x is equal to 0, that's going to be pretty easy. So sine t evaluated from 0 to 0 is going to be, guess what? 0. All right. Well done. Okay. Now we're going to do it again. Sine t evaluated from 0 to pi 6. What would that be? Okay. I believe that's going to be sine of pi 6 is 1/2. That's pi 6, remember, that's 30 degrees, and the x value is square root of 3 over 2, the y value is 1/2, and the sine is the y value. This is on the unit circle. Okay. So that's just going to be sine of pi 6, which is equal to 1/2. And the next one is just going to be sine of pi 4, which is going to be the square root of 2 over 2. Next one would be sine of pi 3, which is square root of 3 over 2. And the next one's going to be the sine of pi 1/2, which is, anyone know that one? 1. Perfect. Okay. Now, I don't know if you remember this or not. Those who were in my class, I hope I told you this little acrostic. For these, our favorite angles of all time, pi 6, pi 4, pi 3. Starting with 0, 0, pi 6, pi 4, pi 3, pi 1/2. Your signs of those is square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2, square root of 4 is 2. So yeah, those are those familiar values. Okay. And notice we were subtracting off the sign of 0 every time, which is 0. Okay, so that's why it didn't contribute anything. Okay. Now, I'm going to erase my chicken scratch if that's okay. Y'all got it? And let's see what they do. You could evaluate 5 different definite integrals, one for each given upper limits, or much simpler just find f of x, or find x, to fix x as a constant, and that would be sine of t, so that would be sine of x minus sine of 0, which is just sine of x, and then plug in, and that's what we did. I mean, I started doing the other, but you saw that it was just going to be sine of that every time. And you just plug in those 6 or 5 values. Sine of 0 is 0, sine of pi 6 is 1/2. Sine of pi 4, sine of pi 3, and finally sine of pi has. And they didn't give you numbers for them, did they? Okay. Yeah, they did. There they are. Okay. 0, 1 half, 2 over 2, 3 over 2. Okay. Now. Okay. You can think of the function capital F of x as accumulating the area under the curve of cosine t, f of t is equal to cosine t, from t going from 0 to x. That's what we're doing. We're adding this part plus that part plus that part plus this part until you got to the end. For x equals 0, the area is 0. Okay? For x equals pi halves, that was, yeah, x equals pi halves is 1, and it gives you the cumulative area under the curve, cosine curve, on the entire interval of 0 to pi halves. That interpretation of an integral as an accumulation function is used often in applications of integration. Okay? Yeah, okay. We'll be doing that next, is applications of integration. Okay? Got it? All right. In example 6, note that the derivative of f is the original integrand. Derivative of sine x is cosine x. That was what was inside the integral. The result is generalized in the following theorem called the second fundamental theorem of calculus. This is the whole point of this. Okay? Yeah, that accumulation stuff, yeah, you can use it, and we'll be using it. But here is the second fundamental theorem of calculus. Okay? If f is continuous on an open interval I containing the point A, then for every x in the interval, and see what's going on there. First, you're integrating from A to x, f of t dt. Then you take the derivative of that. Derivative of an integral is going to give you your f of x. Because this is going to be some function of x, capital F of x, right? Minus f of a. F of a is a constant. Then you take the derivative of that. Well, the derivative of your antiderivative is going to be the thing you started with, evaluating at x. The f of a, capital F of a, is a constant. And you take the derivative of that, and that's 0. So that gives you f of x. So basically, the second fundamental theorem of calculus tells you taking a derivative is the inverse operation is taking an integral. And remember way back in grammar school, we added, then we subtracted, inverse operation. Multiplied, then divided, inverse operation. Raising a thing to a power, taking a root, inverse operation. Logs and exponents, inverse operations. Just on and on and on. Sines and inverse sines, cosines, inverse cosines. You know, one undoes the other. Well, here the whole calculus operation of taking an integral is undone by taking a derivative, and we'll see later that the reverse also works. Okay, so that's the second fundamental theorem of calculus. The first one just tells you how to integrate or evaluate definite integrals. The second one is that the taking a derivative undoes an integral, and you're left with just whatever your integrand was. Okay? Using the area model for definite integrals and the approximation that f of x dx is approximately equal to the integral from x to x plus delta x of f of t dt, that can be viewed as saying that the area of the rectangle of height f of x and width delta x, that's the left-hand side, is approximately equal to the area of the region lying between the graph of f of x and the x-axis on the interval x to x plus delta x, as shown. Okay. So in other words, here's your x plus delta x. And this is your f of x. So f of x times the delta x, the difference in this minus that is delta x.
too big, it's not as great, but it's still a decent approximation. Okay?
Now, let's do that. Use the second fundamental theorem of algebra, of calculus, sorry. We just did example 6. This is example 7 on page 289. Are any of you really hankering to take the integral of square root of t squared plus 1 dt? Is that what your approach was going to be? Hopefully not. You just look at this and say that taking the derivative undoes the integration, and what would that give you as an answer? That's it. Take the integral, the integrand, what's inside there, and plug the x in rather than the t. Because you see, if you could do that integral, it would give you some function of x, right? Then take the derivative of that function, and you should get back to what your integrand was. So that's it. That's the second fundamental. I mean, let's go back and look. Here's, oops. Here. Take the derivative of the integral from a to x of f of t dt. Whatever this is, that's some capital F. And then you take the derivative of that and you go back to little f to evaluate it at x. Just whatever your integrand is, put the x in there in this place. And in our problem, the integrand was square root of t squared plus 1. So put the x in there, you got square root of x squared plus 1. That's it. Done. That's all you do. Plug it in, plug it in. Derivative undoes the integral. The integral is doing something to that square root, but then the derivative undoes what it did, and you're just left with, you just plug in the x instead. X squared plus 1.
But it pretty much undoes itself just by being written that way, right?
What's that?
I mean, it pretty much like undoes itself just by being written that way. Like, I mean,
Yeah.
All you have to do is.
Yeah, exactly. Remember before, we had in the inside cosine x. Antiderivative of cosine x was sine x. And what did I say? You can check this with taking the derivative of that, you get the cosine x again. Same thing here. Whatever the antiderivative of that thing is, when you take the derivative of it, you'll get that thing again. You've got to. That's what the antiderivative, then taking the derivative of it, you get back to what you had. Only thing is you plug in the x. Okay? Now. All right. Let's see what they do on that. Note that f of t is square root of t squared plus 1, continuous on the entire real number line, because there's no place that's going to go negative, right? Whatever t you put in there, square it, becomes positive, add 1 to it, it becomes more positive, so square root of, yeah, so you can do that anywhere on the number line. That's the requirement. So using the second fundamental theorem of calculus, all you do is take that integrand and write it with the, whoa! You can write, they left off the next slide, okay? The square root of x squared plus 1. I don't know where the next slide went. It's not there. Okay. I think that's all they wanted you to do.
Seems like a trap.
Yeah.
It's too easy.
Yeah, just too easy. Yeah. All right. Now, I think they're going to leave off example 8, which is the far more kind of esoteric. Okay, let me erase my ink here, and let's do example 8. All right. Find the derivative of this f of x. Okay, capital F of x is equal to the integral from pi halves to x squared. Or is that cubed? I can't read. I think that's a cubed, isn't it? My eyes are not good. The light's not great here. But I'm pretty sure that's an x cubed, isn't it? Sure looks like it to me. Okay. Of cosine t dt. Okay. We want the derivative of that. Okay. So what we're looking for is d, and they do f prime, which is okay, but then they immediately turn around and make it into d. So why don't we just start with this? D of f of x dx. That's what we're looking for, which would be d by dx of this integral. Pi halves to x cubed of cosine t dt. That's what we're looking for, okay? But let's take this thing over here and say d of f of x dx is d of f, and they introduce a u here, d by du of du dx. Okay? Now you might say, where's the u coming from? Here's where it's coming from. Our fundamental theorem of calculus only deals with an x up here, not an x cubed. So what we're saying here, let u equal x cubed. Okay? With that substitution in, your f of x, which is what you're doing, is d f du du dx. Okay? Well, if u is equal to x cubed, du is equal to 3x squared dx, right? Okay? So du dx is equal to 3x squared if you divide both sides by dx. Okay? Now, what this produces probably should have rewritten this, then it's f of u is equal to the integral. I don't think it really matters what we do here, but this is going to be a u up here. I think we can leave this at pi halves. I'm not absolutely certain this would be cosine t dt. Okay? Nothing changed there. All we did was change the x cubed to a u. Now, I'm not completely comfortable with that, but I think this will be okay. Okay? We didn't change anything on the inside of this, just change the x cubed to a u. Now, d by du of this, that is, we can do that, right? That's your fundamental theorem, second fundamental theorem of calculus. That would just be cosine.
Cosine, you just replace the t.
Yeah, cosine u, right? Yeah. So this part will be the cosine u. And that's what this is right here. So this becomes this, when you do d by du, this becomes cosine u. but u is x squared. So this becomes cosine, I'm sorry, that's x cubed. I keep writing x squared because u is equal to x cubed. Cosine x cubed, but then you've got to do your du dx, which is times 3x squared, okay? Which I like to write it this way, 3x squared cosine x cubed, okay? Now, again, we completely ignored the pi halves there. And we'll see that, and that, we got the same thing they did, okay? But I like to write the 3x squared in front because writing it at the end, it almost looks like you multiply these two together. You don't. This is multiplied by the cosine of x cubed. That's why I like to write it out front. The book wrote it at the end. It's okay. Okay. Now this is how you do it. But what you could have done, and okay, is actually do the integration here. And we can do that. The antiderivative of cosine t is sine t. So that'd be sine t evaluated from pi halves to x cubed. So that would be the sine of x cubed minus the sine of pi halves. And what's the sine of pi halves? 1. So this would be sine of x cubed minus 1. Okay? Now, if we're taking the derivative of that, that's what we're doing, taking the derivative of this, d by dx of that. So d by dx of this would be, what's the derivative of sine? Cosine x cubed, and then we do the chain rule times, what's the derivative of x cubed? 3x squared. And derivative of 1 is 0. So you get that same answer whichever way you do it. Okay? And actually, that's far easier doing it that way than using the fundamental theorem of calculus. But I wanted to show it to you to show that's what you do get. But then if you just did the straight integration, you get the same deal. Same thing. Okay. The deal is that sometimes you can't do that integral. For instance, the one we had before, the square root of t squared plus 1. Not yet. Yeah, later we'll be able to do that when we get the application, but not now. Definitely not now. But this one you could do that integral. Okay. So that's your derivative. That's using the fundamental theorem. All right. With that done, we are now ready to move to the net change theorem, okay, which is sort of an interesting verbiage, how they name it, net change theorem. Goodness, my knee hurts. See, we go to 11:40, so we've got, what, 15 minutes? A little more than 15 minutes. Fundamental theorem of calculus states that if f is continuous on a closed interval a to b, capital F is the antiderivative of f on that interval a to b, then the integral of, this is number 1, first iteration of it, the integral from a to b of f of x dx is f of b minus f of a. That was the first fundamental theorem of calculus, okay? Part 1, however you name that. Because f prime is equal to f, okay? F prime is equal to f, that's how we do it, antiderivative. If this is the antiderivative of that, that means the derivative of this is that. Okay. The statement can be rewritten as the integral from a to b of f prime of x, guess what that means? If you integrate a derivative, you get the difference of their thing. Whatever that was a derivative of, evaluated at those two things. So the quantity f of b minus f of a represents the net change of f on the interval from a to b, of that capital F. And they call it the net change theorem. I can't recall that I've ever seen it named that, but that's what they're choosing to name it. So here's how it states. Net change theorem. If f prime is the rate of change of a quantity f of x, which of course it would be with regard to x, then the definite integral of the f prime from a to b gives the total change or the net change of f on the interval a to b. Okay? Now, notice this is sort of the fundamental theorem of calculus in reverse. The other was the derivative of an integral gives you that thing out here. Now we're doing the integral of a derivative, and that gives you the difference of these two, the net change of that. Well, certainly if you do an integral, you usually wind up with a plus c. Well, that's why you need both of them in there. It's not just one value, but both. Okay? The net change of f over that thing. So here's example 9. A chemical flows into a storage tank at the rate of 180 plus 3t liters per minute, where t is the time in minutes, and t is between 0 and 60. Okay? Find the amount of the chemical that flows into the tank during the first 20 minutes, where t is in minutes. Okay? Okay. That's a rate. That's a flow rate. You could call it capital F, okay, if you wanted to, for flow rate. But if it's a rate, it's the F prime. So that would be your F prime, 180 plus 3t. If F is the flow rate would be derivative of F with respect to time. So that would be your F prime, okay? Where t is a minute, blah, blah, blah. Find the amount of chemical that flows into the tank during the first 20 minutes, okay? So basically what they're saying, and I just chose capital F, it does fit with what we were saying, but it's flow, okay? So let F of t is equal to the amount of flow. So then df dt is the flow rate, the rate of flow. And that is your 180 plus 3t. Okay? Now, find the amount of the chemical flow that flows into the tank. So we're looking for the amount of chemical, which is your F. That's the amount of the chemical. Okay? And so that's what you're looking for, F of t. But the integral, but F of t, well, is equal to a to b of F prime of t dt. Okay? And the integral of a derivative is whatever that thing was. And this is what goes in there. Integral from a to b of 180 plus 3t. Okay? dt. Okay? So yeah, this is example 9. Yeah. And we want the first 20 minutes, so that's from 0 to 20. That's your time interval. So let's do the antiderivative. What does that give you? Of 100, yeah, your integral of this, that'd be the antiderivative of this. What's the antiderivative of 180? 180t, since we're doing it with t, okay? Plus 3t squared over 2. Evaluate that from 0 to 20. So plugging in a 20 there, you get 360, right? Okay, plus 3 times 400 over 2, that would be 600, so that would be 4,200 liters. Because it was liters per minute, so this will give you, and you multiply by minutes, that gives you liters. Okay. Yeah, that's what they got. You see how that works? Okay. So you have to keep your head straight on what's the flow and what's the. Find the amount of chemical. That we really should have gone to that and said, let that be our unknown, and made that alpha of t, which is amount of chemical. I said amount of flow. It was the chemical that was flowing, so the amount of chemical. The df of d by dt is the flow rate, which is what they gave you, okay? And then the alpha of t, the amount of flow, that's what we're looking for, is the integral from 0 to 20, first 20 minutes, of that flow rate times the t. Flow rate, which is liters per minute, times minutes. I mean, yeah, the time interval in minutes, that gives you total flow. That was 4,200. Let's see if they did it any differently. I think they did it pretty close to the same thing, but let's just see. That C of t, I never would have thought of using C of t, but let C of t, I guess for chemical. C of t be the amount of chemical in the tank at time t. How much is in there? Okay, and that's what you're looking for, the amount of chemical in there in 20 minutes. Okay, so that's your C of t. That's what we're looking for. Then C prime of t is the rate at which the chemical flows into the tank, which they told us was 180 plus 3t. So in the first 20 minutes, that would be the integral from 0 to 20 of C prime, which is 180 plus 3t dt, and sure enough, it gives you 180t plus 3 halves t squared, exactly like you did before. We said 3t squared over 2, doesn't matter. That away from there would be 3,600 plus 600 is 4,200 liters. You should have put the units. So the amount of chemical that flows into the tank during the first 20 minutes is 4,200 liters. Okay. Make sense? Okay. All right. Another way to illustrate the net change theorem. How are we doing? We got maybe 5 or so minutes. Another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line where s of t is the position at time t. With s of t is the position of time t, the velocity is s prime of t, right? Change of position for change of time, that's your speed or velocity. Then its velocity is s prime of t, and then your integral would be from a to b. These are times, okay? Speed times time equals total displacement. S of t, S of b minus S of a. Okay, because this is S prime right here. Okay. the displacement of the particle. Where it was at the end minus where it was at the beginning, that's its total displacement. S of B minus S of A. Okay? Do we have time for an example? Oh, wait. When calculating the total distance traveled by the particle, you must consider the intervals where V of t is less than or equal to 0, in other words, where it's going backwards, and the intervals where V of t is greater than 0, because it is going total distance. The other would give you displacement, not taking into account any movement back here, total displacement, final minus initial, whether it went to get there. Okay, so the total distance, you have to take into account all the places where it's negative, and it's moving in a negative direction, and negate that value and add it to when it's positive. Okay? To calculate the total distance traveled, integrate the absolute value of the velocity V of t, which is sort of a pain in the neck, but it's doable. Okay. So the displacement of a particle on interval A to B is just simply the integral. Okay? Oh, okay. Of this, here is the displacement. I said, what in the world are those things? From this graph here. They should have had this at the beginning. Okay? So here your velocity was a positive velocity, then it went negative, and then it went positive again. The total displacement is this plus that, but that's a negative number plus that. So it's this minus that plus that. And that would be your total displacement. Okay? The total distance traveled would be this one plus this value here plus this value there. That takes into account the absolute value of this. In other words, this in effect flips it up and does like this. The absolute value flips that up and makes it positive. Okay? And then you add those three together. Because you see what happened, you were going along like this, then you went back, and then went here again, where you traveled this, this, and that. So that's what adding those does for you. Okay. That's theoretical. Example 10 is going to put it to practice. I have a feeling we're going to have time to do example 10, are we? Sorry, I was expecting to get further today. We got 5 minutes?
Yeah, this is only 11:35.
Okay, all right. You want to try it? Okay, the velocity in feet per second of a particle moving along a line is, that's your velocity. T cubed minus 10t squared plus 29t minus 20. Okay? T is measured in seconds. Okay. What is the displacement of the particle on the time interval 1 to 5? That's the simple integral, right? Displacement is simply the integral from 1 to 5 of this. T cubed minus 10t squared plus 29t minus 20. Okay. At least somewhat simple. You just do that integral. What's the antiderivative of that? T4 over 4 minus 10 to the third over 3, right? Right, don't. Okay. Plus 29 t squared over 2 minus 20t. Evaluated from 1 to 5. Still not going to be a piece of cake, but okay, does anyone know what 5 to the 4th power is? 625, okay? So that'd be 625 over 4 minus, and 5 cubed is 125 times 10 would be 1250 over 3 plus 29 times 25 over 2 minus 20 times 5. Okay? Minus 1/4 plus 10/3, because that's 1. It's pretty easy to calculate. Minus 29 over 2 plus 20. Okay? Pull out your calculators, please, and do this. Now, there are some things that can simplify. That would be 624 over 4, because you subtract 1/4 from that, and I bet you that is a whole number. And this would be 1240 over 3, which I don't think is going to come out even, but you could try that. And that would be 24 times 29, but you can just do it on the calculator, and that would be minus 80, I think. Okay. So yeah, it could be done a little bit easier on the calculator, but you can still do it that way. Do you get an answer?
$32 over 3.
32 over what?
Over
3. Hey, that's exactly what they did. 32 over 3. Okay? Are we going to make it? What is the total distance traveled by the particle on the time interval 1 to 5? Okay? And they say do the absolute value of that, and that's still not an easy thing to do. You have to basically draw your graph of that function there. Yeah, that's the only way I know to do it. Okay? And they do it for you in the book. Let's see if they show it to you. Okay, the particle moves a total of a little less than 10 feet to the right. Okay, here's how you do the total distance traveled. Okay, oh, clever them. I never would have thought to factor it, but you can do that. Okay, wow. Clever them. I'll just say that again. It is 0 at 1, at 4, and at 5. From 1 to 4 it's positive, and from 4 to 5 it's negative. So with that in mind, you can integrate this part and then integrate this part separately, and that come up a negative number. Take the absolute value of it and add those two together. Okay. Do we have time for that?
I was just reminded that it was 11:40, it's 11:41 now.
Okay. So can you do that on your own, or you want to do that when we come back to class on Monday?
Probably going to come back to class on Monday because we still have people missing. Maybe we're going to.
What's that?
Probably going to do it next time.
Okay. Okay, so you do want to do that. So let's do the B part next time. Let me find my pencil. Somewhere I had a pencil here. Oh, there it is. There it is. Cleverly disguised as a pencil. Okay, we'll do the B part next time. We came close to finishing the section. I mean, that close. So homework exercises 5 or 7, and they're both at calcchat.com. Odds 9 through 35, they're all at calcchat.com. 19's at calcview.com. Do either 37 or 39, they're both a calc chat. 37 is a calc view. Do any of the odds 41 to 45, they're all a calc chat. 43 is a calc view. Do any of the odds 47 to 51, they're all a calc chat. 47 is a calc view. Do any of the odds 53 to 57, they're all a calc chat. 53 is a calc view. And then do some of the odds 59, 61, either 59 or 61, they're both a calc chat. Do 63 is both a calc chat and calc view. Do 65 is a calc chat, but not a calc view. Do 67 is a calc chat. And then do any of the odds 61 to 73. They're all at calc chat. 71's a calc view. 75 to 79, they're all at calc chat. 75's a calc view. 81 to 85, they're all at calc chat. 87, 89, do any of the odds 87 through 91. They're all at calc chat. And then you can try doing 93 to 97. The B part of that, you may not be able to do, but the A parts you can. And they're all at calc chat. 93 is at calc view. We'll pick up the rest of that next time. Okay. Good deal. All right. Seems like I just saw you now say have another good weekend. Okay. What this is going. Huh?
I said, oh yeah, because we wasn't here. I said, oh yeah, because we wasn't here.
Yes, exactly right.
How was your Labor Day?
It was nice. Yeah. When we were packing up to come home, I was lifting the cooler, walking upstairs, and I sort of pulled the muscles, but it's almost completely healed by now. But that was the only negative thing of it. So,
See you today.
all right, you too. Thanks.